Oops, hi again, guys. Sorry about that little technical hiccup. Continuing where we left off, we were trying to see how the relationship between a function and its inverse. So we plug 0 into the original function. The output is -6. We see that when we put -6 into the inverse function, it spits 0 back out at us. Same with 5 and 14. We put 5 in, we get 14. We put 14 into the inverse, it gives us 5 back. So we could continue this indefinitely, but the only way to prove, there's two ways to prove a function and its inverse are actually inverses of each other. First of all, we could use every number in the domains and see that this relationship holds. But the domain of y equals 4x minus 6 is all real numbers. We'd sit here for a very long time. So algebraically, to prove that f and f inverses of each other, you must show both things. You must show two things. You must show, number one, that when you compose f with f inverse, it just gives you back what you started. So if you take the output, put it back in, you get the input that you started with. And you must show the other relationship. If you stick -6 into here, you get 0. You put 0 into the original, you get -6 back. So in order to prove a function and another function are inverses of each other, you have to compose them and show that it all cancels out and we just get what we started with. So let's show that with this guy. Let's prove 4x minus 6 and x plus 6 over 4 are inverses of each other. Note, these are the same. I just wrote it. I guess I can do this, x over 4 plus 3/2, right? So you can use either one. So one, let's show that f of f inverse, when we work out the algebra, they're just going to cancel each other out. So that is, I'm going to take this function and I'm going to stick it in here for x. I'm going to replace x with the entire inverse function. So it's going to be 4 times the inverse function, x divided by 4 plus 3/2. So I'm going to do the algebra. We're going to distribute the 4. 4 times x over 4 is x. And then 4 times, oops, I lost the -6. Silly me. Holy cow, don't forget that. All right, sorry. I'm still a little baffled by my little technical glitch there. All right, so we're replacing the x with x over 4 plus 3/2. So we're going to put x over 4 plus 3/2 right here, and I'm going to subtract 6. So don't forget the -6. I'm going to distribute the 4. 4 times x over 4 is 4. 4 times 3/2 is going to be 12/2. And then we're going to subtract that 6. So this is x plus 6 minus 6. And as expected, that just canceled out nicely and gave us back what we started with the x. All right, now we have to do the composition in the other direction. It's just the rule. We have to show that they're inverses of each other. So this time, I'm going to take this function and stick it in where I see x here. So it's going to be 4x minus 6 all over 4. So I'm putting the whole function right there, plus 3/2. Right, and I'm going to break this up. This is 4x over 4 minus 6 over 4 plus 3/2. But 4x over 4 is just x. 6/4 is 3/2 minus 3/2 plus 3/2. And that just equals x. And if you found the inverse function correctly, those will always cancel and you'll always result with just x because they undo each other. All right, let's do the algebra for a slightly more complicated function, a rational expression where x appears in more than one spot. So let's follow the rules. 1, we're going to replace f of x with y. So it's going to be y is equal to 2x minus 3 all over x. Second step, switch x and y. All right, and now we're going to solve for y. So x is equal to 2y minus 3 all over y. So suggestions. If you have y in multiple places, or even if you have fractions, I would suggest eliminating the fraction. We can do that simply by multiplying both sides by y. And this just becomes xy equals 2y minus 3. So it's a lot easier to work with equations that don't involve the fractions. Now, when you have multiple y's, now remember we want to just get y equals everything in terms of x. So the trick is when you have multiple terms with y's, first of all, eliminate fractions, eliminate parentheses if necessary, then look at your terms. If a term has a y in it, bring it on one side of the equation. If it doesn't, either leave it or bring it over to the other side. So what I'm going to do is subtract 2y from both sides. And I'm going to get xy minus 2y equals -3. And the whole point of bringing all the terms with y's over is you can turn multiple y's into a single y by factoring out. We're going to factor the y out, and we're going to get y times x minus 2 equals -3. So we started with an equation that had 2 y's. By bringing all the y's over to one side and eliminating fractions, we got y times x minus 2. Now we can divide out that x minus 2. And we solved for y. Y equals -3 over x minus 2. Right, and then just for the record, there's an awful lot of negatives here. This is not incorrect, but typically what you'll see, you'd see the answer in the back of the book like this. Instead of leaving the numerator as a negative constant, we would multiply the top and the bottom by -1 and would get +3 all over. Well, x minus 2 times -1 becomes 2 minus x. So either one of these is perfectly correct. This one is just more visually pleasing. So the inverse function is equal to 3 over 2 minus x, or equivalently -3 over x minus 2. All right. So f inverse of x is going to be 3 over 2 minus x. All right, so just a couple of reminders here. The domain of a function, of a rational expression, remember the denominator can't be 0. So if we look at f, we know the domain is all x's as long as x does not equal 0. So that's set notation. Equivalent interval notation would be from -infinity to 0 and 0 to infinity, so to the left of 0 and the right of 0. The domain of the inverse, well, if we treat this as its own entity, the denominator can't be 0, and 2 would make the denominator 0. So it would be from -infinity to 2 and 2 to infinity. Now, just a friendly reminder, there is a relationship between the domain of a function and the domain of an inverse and the ranges. Remember how we found the inverse function is we just switched the roles of x and y. That's what inverses are. They're the same equation. We're just switching the roles of x and y and solving for y. So if we know the domain of a function, we automatically know the range of the inverse because the range of the inverse comes from the domain of the original function. So the domain of the original function is x cannot be 0, then the y's in the inverse cannot be 0. So the domain of a function is equivalent to the range of the inverse. So in interval notation, it'd be -infinity to 0, union 0 to infinity. The domain of the inverse is going to equal the range of the original function. If the x's can't be 2 in the inverse function, then the y's cannot be 2 in the original function. There's no input here that will produce an output of 2. So -infinity to 2, union 2 to infinity. So remember the domain of a function is equivalent to the range of the inverse, and the range of a function is equivalent to the domain of the inverse. So I'm going to leave this as a challenge problem here to prove. To do, I'll give you 3 bonus points towards your final grade. Scan in and send before next Thursday. (9:10) before class. So as long as I get it before our class time, I will take it and grade it and assign bonus points if appropriate. All right, so just a couple refreshers. Only one-to-one functions have inverses. A function is one-to-one if each input has its unique output. That is, outputs don't repeat in one-to-one functions. Graphically, one-to-one functions pass the horizontal line test. The domain of a function is equal to the range of its inverse, and the range of a function is equal to the domain of its inverse. All right, one little last tidbit of information. Let's take into consideration this function. Let's look at 2x squared minus 3. Now, as is, this is not one-to-one. So we could just stop and say, well, this function does not have an inverse. As is what I meant to say. As is, this is not one-to-one. Thus, no inverse. Unless we restrict the domain. Right? So if I cut off a piece of this function and only leave what would result in a piece that passes the horizontal line test, this function would be one-to-one. So let's consider the function f of x equals 2x cubed minus 3 on the interval. What if we just look at this piece of it right here? And we disregard this. So if we only look at it from 0 to infinity, it's now one-to-one. We could have looked at it from negative infinity to 0, but I kind of liked working with the piece on the right. So we can now find its inverse. Right? So this is our restricted domain. By restricting the domain, we create a function that has an inverse. So I'm going to write it as an equation. Whoops, 2x squared. Wow, sorry, I must be getting tired. 2x squared minus 3. We're going to switch x and y. X is equal to 2y squared minus 3. And we're going to solve for y. So we're going to have x is equal to 2y squared minus 3. We'll add 3 to both sides. X plus 3 is 2y squared. We're going to divide out the 2. I'm going to put the y squared over here. X plus 3 all over 2. And then we're going to take the square root of both sides. And y is going to be the square root of x plus 3 all over 2. So we have f of x equal to 2x squared minus 3. Domain of f is going to be equal to 0 to infinity. We had to restrict it. And if we go back and we look at the range, we can see that the range is from 3 to infinity. Oh, sorry, negative 3 to infinity. Be careful, it's below the x-axis. And f inverse of x is going to be the square root of x plus 3 all over 2. The domain of f inverse is going to be the range of the original function. If you think about it, it makes sense. The smallest value we can input here would be negative 3 because then we'd take the square root of 0. And the range of the f inverse is going to be the domain of the original function, 0 to infinity. All right, kids, have fun with these problems, and I will see you soon.